let's talk about, we talked a little bit about double sideband suppressed carrier generation, which was basically through the use of a mixer. So this is easy. There's not much to talk about here. A switching modulator is, of course, another way of producing double sideband signals indirectly through multiplying the signal by a square pulse train and then filtering the result. Now, how about demodulation? Well, of course, mathematically speaking, you can take the signal, multiply it again with the carrier wave, and then low pass filter the result. And this should work. So how do you get the carrier signal is the main issue here. How do you obtain the carrier signal at the right frequency, at the right phase? This is done using a structure called a phase lock loop, PLL. It is a feedback system. It's essentially a control loop that we will go a little bit into the details of later on in this class. And what it does is it matches to the frequency of the received signal. It also matches to the phase of the received signal. And when we low pass filter the mixing result, we obtain the original message signal in theory, of course. Now, of course, this assumes a lot of idealized things, like the received signal is exactly the same as the transmitted signal. The PLL works perfectly, and the low pass filter has ideal gain in the message bandwidth, etc. Okay, and this is the mathematical representation of this phenomenon. This is the modulated signal. This is the carrier coming from the local oscillator. The low pass filtering provides the original signal. Now, the low pass filter's ideal characteristic can be relaxed. The higher this carrier frequency is, the easier it is to relax this filter's characteristic, of course, because the components that we would like to attenuate are much farther in that case than the band that we're trying to accept. Okay. So last time we discussed what happens if the detector's local oscillator has a frequency mismatch and a phase offset. Now we saw that the frequency offset causes a modulation in the output, and that is detrimental in the case of voice, for example. The phase offset, we said, is less important, especially in terms of average human hearing. The phase offset is unimportant. Okay, so how about carrier recovery? As we said, so this frequency offset will cause a distortion. This is a problem not only in analog communication, but also in digital communication. So we should try to get a good replica of the carrier at the receiver. How can we do this? First, let's talk about the squaring loop structure. Now, the squaring loop is a loop that uses a phase lock loop that we just discussed. It uses a PLL, or it uses a limiter. So let's try to take a look at what this diagram of the system does. So U of t, the modulated signal, comes in. Now, what do we want? We want to have a cosine 2 pi f ct to input as input to this mixer. How do we generate that? We will generate it using the input signal. First, we use a squaring device. It is a nonlinear electronic circuit. Okay, using like just a single diode also, even the simplest nonlinear electronic component, right, could possibly do. So we, once you get a nonlinear electronic circuit that produces second order components, you can then use it as a squaring device. What would you do? You would only use a second order component through appropriate filtering. But for now, suppose the squaring device is exactly doing the squaring, eliminating all the other higher order terms, eliminating any DC term, etc. Sorry, I shouldn't have said DC. In this case, essentially, we have the square of the message plus the square of the message multiplied by cosine, and the message itself, if it had DC, we would have DC here at the output. Never mind. What I mean is any third order components, any first order components are eliminated after the squaring device. When we now input this to a bandpass filter centered at 2fc, okay, we get rid of m squared of t, and we are left with m squared of t times cosine 4 pi fct. Now we can let a limiter to log on to this. Okay. Now, what was the function? What is the function of this? It just turned everything into a positive, turned the message essentially into a positive valued waveform. Now we feed this into the PLL. Okay. And the PLL, it locks on to the carrier here, which is 2fc. And we will, as I said, we will go a little bit into the structure of the PLL later on. Now that you have 2fc, passes through a frequency divider, that's another circuit, and you have your carrier. Put the mixing result into the low pass filter, and we have our demodulated signal. Now that's so basically that's a method for demodulating double sideband. As you can see, it requires some electronics, and this thing was not even possible in the early days of communication back in the 1920s, 30s. Okay, so when people came up with amplitude modulation first, they didn't come up with this method. They invented something much simpler, and that is conventional AM. Okay, conventional AM is not going to require carrier recovery. It doesn't require any synchronization. Okay, now, even now, there are certain situations where you may want to go for an unsynchronized scheme, a simple scheme. And this idea might be helpful when you're not really after a lot of power efficiency. And you'll see what I mean in a few minutes. The idea is add the carrier on top of the double sideband spectrum. Okay. Essentially, when you put the carrier on top, you are helping the receiver by sending what it needs for the modulation along with the modulated signal. Okay, so let's see. Remember, the double sideband suppressed carrier part is m of t times cosine 2 pi fct. Now, we are also adding a scalar, a DC term onto the message, and then multiplying with the cosine. So then we are basically adding the cosine AC times cosine 2 pi FC term on top of a scaled version of double sideband suppressed carrier. Okay, so m of t cosine 2 pi fct times a scaling coefficient Ka plus AC cosine 2 pi fct. Ka is referred to as the modulation index. As you can see, it controls how strong, how powerful is the modulated waveform with respect to the carrier. Okay, now when we convert to frequency domain, we have the original double sideband spectrum plus the delta functions, the impulses at Fc and negative Fc. Any questions? Is this okay? Okay, in the next hour, I will try to make my iPad work so I can draw on this. Yes, please, question?
Hocam şurada KA'ler yok sanki ama bana mı öyle geldi?
Oh, you're right. You're right. The KAs have flown off, so I should add them in. Unfortunately, so, well, at the moment, I cannot edit this, but I will revise them and post them on Note to class. Thank you. Okay, so this is m of t, the message. Suppose this is the spectrum. The modulated waveform is going to look something like this. Okay, so instead of remember what happened when we directly multiplied m of t with the carrier? There would be oscillation on top that matches the shape of m of t. Now we're taking m of t and raising it up by a constant. Essentially, we take Ka times m of t, add 1 to this. Okay, so rise it up. And then we multiply by u of t. Okay, so you can see the envelope of the modulated waveform looks like the shape of the message, except it's raised up. Okay, and depending on how large Ka is, whether or not the negative part is going to stay above, so this edge, this point here, is going to rise up if we make Ka sufficiently small, right? It's going to be 1 plus Ka times this negative value. And if Ka is small enough, 1 plus Ka times this negative value is going to be above the horizontal axis. This means that this shape will be exactly replicated as the envelope of the modulated waveform. And that is the key for the easy recovery of conventional AM signals, which is called the envelope detector. Maybe you have heard of the envelope detector in certain electronics lab courses. Have you? Right. It's a simple circuit. The idea is, as I was trying to explain, if you take the maximum amplitude of M of t, the message signal, because that would be what is causing trouble, right? If we think of the maximum negative value, for example, and if Ka times that value is less than 1, then it is guaranteed that 1 plus Ka M of t is always going to stay above 0. And in that case, the envelope of the modulated signal will look exactly like M of t. Otherwise, if this inequality is not satisfied, when we multiply by the cosine, the positive and negative components of 1 plus Ka M of t are going to interfere, causing the shape to be different. In that case, the envelope cannot be used to demodulate the signal. Okay, so then provided that this condition is met, all we have to do is extract the envelope, and you know that is possible with an envelope detector. First, let's make a definition. Let's call this part AC times 1 plus KAM of t by the name A of t. It is like some amplitude waveform, A of t. Now, the envelope detector, what it does is so basically it tracks an oscillating waveform such that it passes the positive cycle and then kind of decays during the negative cycle. So look at this very simple circuitry. Let's feed an AM waveform here. When the AM waveform is in its positive cycle, the diode is on, and at the output we see the waveform itself. Right? When the waveform switches polarity, the diode is cut off. What will happen? The capacitor, which has filled up to the last value of the signal before it switched, will start decaying over the load resistance here. Okay, now you may say, well, how fast it decays? How fast it decays is an issue that will control how well this envelope detector works. Is this clear? Okay. Now, let me ask you, how fast does this thing decay?
Depends on RC.
Exactly. RC is the time constant. So the larger the, let's see. Switch to more. Okay. Let me switch to this slide. So when RC is small, okay, the decay is quite fast. Okay, because the time constant is small. When RC is too large, okay, the decay is slow. That will cause essentially a tracking failure. The envelope detector is not going to very successfully track the envelope when the RC is too large. When RC is too small, time constant is too small, then there's going to be too much ripple. Okay, ideally, we want the ripples to be smaller. Okay, so that is definitely then a design consideration. You want to pick some RC somewhere in between. Has to be definitely much less than okay, think about the following. 1 over the time constant should be larger, 1 over the time constant, essentially the frequency of this ripple must be larger than the bandwidth of the message, but should be smaller than the bandwidth of the carrier. So ideally, we want RC to be in between 1 over FC and 1 over FM. FM stands here for W. But I mean, FM, it actually comes from assuming that the message signal is also a sinusoid at frequency FM. Okay. Now, let's go back to the concept of overmodulation. As I said, when Ka m of t in absolute value is larger than larger than 1, then AM, conventional AM, is not going to work because there's overmodulation. An example is here. The bottom curve is an example of overmodulation. The positive and negative envelopes sort of interfere, and the resulting resulting modulated carrier does not have an envelope that looks like the message signal. So the limiting case that is barely possible to demodulate by an envelope detector is the 100% modulation case, where Ka times m of t is equal to 1. Often we desire, of course, for modulation to be less than that. For example, this is the 50% case. Okay, and we can define a modulation index using this Ka. Such that because we now we want something that will characterize different regardless of what m of t, we want a modulation index to work irrespective of the amplitude of m of t. So we can design this modulation index parameter such that the modulation index divided by the maximum magnitude of m of t is equal to Ka. So the modulation index is Ka times the maximum magnitude of m of t. So that means that we want the modulation index to be less than 1. To prevent overmodulation. Okay, so my question to you is, what would prevent us from making the modulation index arbitrarily small? Why wouldn't, is there a problem with making it 0.1, for example, as opposed to 0.5?
The signal may become too small.
Excuse me?
The signal may become too small to process.
Exactly. It will be very inefficient because suppose, okay, so this Ka divided by the maximum magnitude is very small. Okay, so this maximum value of Kam of t will be small with respect to the 1. So when we're transmitting, we're using most of our energy to just send no information, just the carrier. And that is going to be very inefficient. And it is going to be especially bad when there's noise. In the first part of our class, we are ignoring the presence of noise, but there is always noise, right? In electronics, when you're trying to pick up a signal. And the higher the power in the signal component, the more immune, essentially, we are to noise, right? And so, therefore, making Ka or making mu A, modulation index, too small will be a problem in terms of power efficiency and in terms of noise immunity. Okay. All right. Now, let's come back to the discussion of the frequencies, Fc versus W. W, if you know, if you remember, is the bandwidth of the signal, input signal. Now we want Fc to be much larger than W so that the envelope can be followed. Because you know, it is visually clear that the larger the Fc, the more visible the envelope. Of course, then you have to arrange your time constant of the envelope detector accordingly. Okay. So this condition, Fc much larger than W, is called the narrowband mode. A lot of communication is done in the narrowband mode. Okay, a lot of classical communication, at least. We talked about this already. RC controls the exponential decay. So R times C is a time constant. And small RC, as I said, results in a lot of ripple. Large RC results in a failure to follow the envelope. Let's talk now about the power efficiency of amplitude modulation and double sideband suppressed carrier. In order to do that, let's imagine that we are transmitting this double sideband suppressed carrier signal across a 1 ohm load. Okay, how much power would we be transferring to this 1 ohm load over, yeah. So basically energy averaged over time, right? So this is our message. I mean, think of it as the voltage, right, across the resistor. And it's just a resistive power, so you would just square it, V square R, right? R is 1. So square the voltage, you get the power. Now integrate it in time. and divide by the length of the time window. Take the time window duration to infinity, that gives you average power. Okay, now let's expand this product. Cosine squared is 1 plus cosine 4 pi FCT, right? So when we multiply and express the result in additive terms, the first term is the square of the message integrated, and the second term is the square of the message times cosine, a cosine at frequency 2f, see? Okay, now, when we, so by our narrowband condition, the cosine at frequency 2f is much faster compared with the message. So this is a very so the normally, if you didn't have the message here, and if you integrated the cosine, what would you find? 0, right? If you integrate the cosine over a period, you will get 0. Now, since the message is very narrow band with respect to the cosine, it's not really changing much, and the result is close to 0. This is the narrow band condition. On the other hand, our signal has a power equal to PM. Okay, so the result of this summation then is AC squared over 2 times the power of our message. So the transmitted power then is AC squared over 2, where AC is the carrier amplitude, times the power in the message signal. Okay, any questions here? So since classes now are based, you will see that the power efficiency for conventional AM is not very good. So the transmit power we computed already. Let's go back to the previous slide. For double sideband suppressed carrier, we computed transmit power as AC squared of over 2 times PM. PM is the power in the message signal M of T. Okay. Now let's leave this aside and let's compute the transmit power in AM. Okay, so we have 1 plus mu A MN. This stands for, so basically in the previous definition we had Ka times M of T here. We replaced by mu A times the normalized version of the message. Okay. So let's use this to compute the power as before by expanding the cosine squared into 1 plus a cosine of twice the frequency, and expanding the terms, we have the square of 1 plus mu A Mn of T plus this high frequency component. By the previous argument, by the narrow band condition, because the variation in the first component, in the multiplicative component, is very slow with respect to the cosine, it's as if you're computing the power in the cosine. I mean, but you're not computing the power in the cosine, I'm sorry, you're integrating a cosine. If you computed the power in the cosine, you would have cosine squared, which would give you a positive power. But this corresponds to integrating a cosine, which will give 0. Okay, so this term is approximately 0 then. And we have this term to worry about. And now let's look at that by breaking it into 1 plus the mu a mn of t squared terms. And there's a cross term, of course. So this is the cross term. Now the cross term, we will argue, also gives us 0 if the message signal has 0 mean. You might ask, are we allowed to assume that the message signal has 0 mean? What is your answer to that? How would you answer that if someone asks, is it okay to assume that the message signal has 0 mean?
No, in general, no.
Well, in principle, no, but if you think about it, why would you transmit a DC? Right?
Mhm.
Why would you transmit? Why would you spend your power to transmit a DC? So this is, in fact, a good assumption in general, that the message is 0 mean. So that takes care of this term. This is 0 then. So we have the first two components. The first gives us AC squared over 2. And the second gives us AC squared over 2 mu A squared PMN. Okay. So in contrast to the double sideband suppressed carrier, we have an additional term due to the DC component. The additional term is this one. The additional term is this component, the first component. Style stuff, right? Okay. So how about the power efficiency? Efficiency is defined as the useful power divided by the total transmitted power. What is the useful power? The power that corresponds to the message. In double sideband, all the power is used to transmit the message. So the power efficiency is by definition 100%. Okay, that of course is under completely ideal circumstances, does not refer to the efficiency of the whole transmitter receiver architecture. It just refers to the efficiency of the mathematical operation we're doing in this modulation scheme, because all the power is transmitted to send the signal. This is the transmit power. It's AC squared over 2 times PM. In AM, though, the transmit power has a component due to the message and a component, let's see, due to the carrier. Therefore, the efficiency is going to be less than 100%. How much is it? It depends on the value of this mu A. Now, this efficiency is usually small since we're going with the square of mu a, right? So what is the efficiency? Mu a squared PMN divided by 1 plus mu a squared PMN when you cancel out the AC squared over 2. And depending on the value, so if PMN is around 1, for example, and if mu a is 0.5, then this will be 0.25 divided by 1.25, right? Which is what? 1 over 5, right? 20%, which is pretty small as an efficiency. Okay, so significant power is spent on transmission of the carrier. And that's the main drawback of conventional amplitude modulation. What is the plus side? What is the advantage of conventional modulation? It allows easy demodulation with an envelope detector. Okay. So far, so good. Any questions? Now, we will talk about something called single sideband AM modulation. Remember, when we first talked about the double sideband suppressed carrier modulation, I said that it was bandwidth inefficient. Why? Because you take this signal, there is a, suppose this part is blue and this part is red. When we modulate with double sideband, we put the, oops. We put the signal, the blue and the red parts, okay, essentially, the blue and the red parts repeat. In other words, if you were just, able to somehow get the upper sideband only and bring them together, you would be putting the blue part and the red part together, right? Okay. So that is the idea behind SSP. Why transmit both sidebands? Just transmit either the upper sideband, this is the upper sideband, or transmit the lower sideband, which is this one. Okay, how are we going to do this? Of course, everything I said is only for a real valued signal. If your signal was not real valued, then the spectrum wouldn't be symmetric like this, wouldn't be conjugate symmetric like this, and we wouldn't be repeating information in both sidebands. But at the moment, we're talking about real valued signals. So as you know, when M of t is real, the Fourier transform is conjugate symmetric. And as I said, the transmission of both sidebands is redundant. Okay, so the baseband signal, when modulated with DSP, is the composition of an upper sideband signal, which is the outside here, the upper sideband signal, and the lower sideband signal. This is the lower sideband. It's given here. It is sufficient in terms of the sending the same amount of information to transmit either the upper sideband or the lower sideband. Okay, so in that way, we would be using the bandwidth more efficiently, be able to fit more signals into the spectrum with no loss of information. Of course, there's going to be some additional processing needed, like better filters, etc. We will come to that. Now, SSB is still in use today at low frequencies in military and in shortwave radio broadcast from faraway places. For example, look at these bands, 49-meter wavelength, around 5.9 megahertz bandwidth, channel bandwidth. I mean, not the bandwidth, sorry, the center frequency. Okay. So you can, why do you think these low frequencies, like low megahertz range, is used for long distance radio broadcast? It's an easy electromagnetics question.
Range increase.
Yes, please.
Range increases when the center frequency decreases because
Yes,
the
so
attenuation is
attenuation is
low.
less, right? Well, at these long wavelengths, the propagation goes over longer distances without attenuation, because attenuation increases with frequency usually. Okay. So there are some huge transmitter components and huge antennas corresponding to these large wavelengths. They're called shortwave. They're on the order of several tens of meters, right? So definitely large components are needed. Like, these are not your typical radio components at the transmitter. Okay. So let's now see the mathematical representation of SSB. It's really quite fascinating. So in frequency domain, this is really easy to think about. So let's start from the frequency domain. What I want is just eliminate so basically, let's go back. Let's go back. What I want is a filter that gets only the upper sideband or the lower sideband. So let me go back to our original color scheme. So we have the red part and the blue part, right? So in the upper sideband, if we're choosing upper sideband, we want a red here and we want a blue there. So how can we do that? Well, let's first start at baseband. At baseband, if I want to capture this blue part, I need to use a filter, a strange filter that looks like this. It has a sharp cutoff exactly at 0. It does not pass the negative. Of course, this is not a real valued filter, right? This is a complex filter. What does that do? You can replicate it by using the signum function. What is the signum function? The signum function is -1, 1, right? Before and after the origin. So essentially, you need to divide it by 2 after you add the 1. So because the signum function is +1 -1, and 1 plus the signum function would be at 2, but if you divide it by 2, you get 1 plus signum, which is exactly the filter we're looking for. Okay. So let's call this the pre-envelope, the positive pre-envelope of this. It's not called pre, let's call it M plus. Okay, M plus is M of F times 1/2 1 plus signum F. Now I can always write the signum function as -j² times signum of F, right? Because -j² is 1. Okay, but then you will recognize this j times signum of F from before as the Hilbert transform. Okay, the Hilbert transform is a 90-degree phase shifter. In time domain, it corresponds to taking a signal and convolving by 1/πt. But in frequency domain, it's perhaps easier to see. The Hilbert transform of a signal y of f is -j signum of f y of f. Okay, so then M plus, which is the blue part, is nothing but, let me see. I'm just gonna take another pen. So this is equal to, I want to take a, okay, maybe, yeah. So M of F over 2 minus J M of F over 2 times signum of F, which is equal to 1/2 M of F plus J over 2 M Hilbert. Any questions so far? So the blue part, which is M plus of F, turns out to be M of F over 2 plus J over 2 M Hilbert. That's it. We got the blue part. What do we want to do? We want to translate the blue part to FC. And we want to translate the red part to negative FC. So we also need the red part. Okay, so far we have the blue part in frequency domain. How about in time domain? In time domain, well, it's here. By direct conversion to time, it's here. But at the moment, let's continue in frequency domain. So how about the red part? This is exercise for you. Show that the red part can be expressed as m of f over 2 minus j over 2 m Hilbert. Correspondingly, in time domain, it is 1 over 2 m of t minus j over 2 m Hilbert of t. Now, m Hilbert and m are real valued functions, real valued signals. M minus and m plus of t are both complex valued signals. Clearly, because their spectra are very uneven. Okay. Now, when we put the spectra of m minus and m plus together, translated to Fc and minus Fc, suddenly we have our upper sideband. It's like magic. Okay, so m plus f minus Fc, so the blue part shifted to the right, m minus f plus Fc, the red part shifted to the left. When we add them together, we get our SSB signal. In particular, it's SSB USB. Okay, how about in time domain? A shift operation. Okay, in time domain, it corresponds to taking m plus e to the j 2 pi fct and m minus e to the minus j 2 pi fct. Any questions here? Are you all following? And you thought modulation was multiplication. Okay. Now modulation suddenly become more sophisticated, right? Now, notice that, I mean, we will stop using this m plus and m minus and switch to the language of Hilbert transform now. Here is how we will do it. Notice that the Hilbert transform of a real signal is real, okay, because it's just convolution by 1 over pi t. Then m minus is nothing but the complex conjugate of m plus. Why? Because look at how m minus is written. M minus is this, and m plus is the same thing with this replaced with a plus. Okay, and since this is real, m minus is the conjugate of m plus. But then here we have m plus e to the j 2 pi fc t and m minus e to the minus j 2 pi fc. So this is m plus e to the j 2 pi fc t plus m plus conjugate times conjugate of the. So basically this is twice the real part of m plus e to the 2 pi fc t. Okay, but now write m plus in terms of the Hilbert transform. It's 1 over 2 m plus j over 2 m Hilbert. And also expand the complex exponential as a cosine plus sine. What do we find as a result? By multiplying out the terms, The 1/2 will cancel with this 2. As a result, we are going to get m times cosine minus m Hilbert times sine. What do you think we've done? I mean, we've been through a lot of math, but eventually we came to something that looks a lot like double sideband. The first component here is double sideband. This is the DSP. The second component is like a DSP, except we're using a sine rather than a cosine, and we're using the Hilbert transform of the message. So we are doing something quite interesting. We are removing the unnecessary information that is transmitted. Essentially, the resulting signal is still real. We've gone through some complex analysis to get here, but the resulting transmitted signal is still real. We've done everything for the upper sideband, by the way. We could have repeated it for lower sideband. So as exercise, derive this expression, derive the lower sideband expression. Just the same way we've derived the upper sideband expression. Any questions?
Hocam ST real mu oldu yoksa kompleks mi? ST dediğimiz değil.
SOT is real. Because M Hilbert is real. This term is real. And if you think about the spectrum is symmetric.
Hocam,
It is.
burada mesela filtredeki signal'larda falan bunu fiziksel olarak düşündüğümüzde double sideband'de mixer'dan geçtikten sonra bandstop filtre koysak yani ifade olarak aynı şeye denk geliyor sadece.
Yeah, that would be a way of generating single sideband. Yes. You could do it that way. That's one of the ways for generating this generating SSB. You could. It's easier to do that when of course, if you think about it that way with a bandstop filter, you realize that you probably want a DC null at M of F, the original message signal, right? In general, for SSB to work well, you want no DC actually, because otherwise it's hard to implement that very sharp filter. We'll come to that, but you're right. Any questions? Okay, so generation is exactly what you said just now. This is called the filter discrimination method. So generate double sideband and then filter out the unwanted sideband. But a practical filter cannot be infinitely sharp, so M of F should have a DC null. Now, voice signals, I mean, historically, SSB has worked well for radio broadcast of voice, of sound, because as humans, we don't, when we talk, we don't produce output near zero. Okay, we are, typical human voice starts around maybe 300 hertz, goes to around maybe 3.4 kilohertz. So there is a natural DC null here. Let me write the name DC null. So that is convenient for the filter discrimination method for generating SSB. But of course, the filter transition bandwidth, suppose it's 2FL. We want FC to be much larger than FL, in order to get a filter that's not excessively sharp. Okay, so let's deal with some practical issues related to SSB modulation. This main practical issue is what to do to deal with this requirement of a sharp. So how do we get over this requirement of a sharp bandpass filter? Well, the idea is an idea that will resonate throughout all of communication system design, which is divide and conquer, the usual divide and conquer idea. Let me write it here. Divide and conquer. When you have a big problem, split it out into multiple stages and solve each small problem one by one. So here, the way we divided this problem into stages is first do SSB modulation at a lower carrier frequency, and then at the lower carrier frequency, it's easier to generate. It's easier to design a sharp filter. Okay, in your electronic and analog electronics classes, you have seen some trade-offs. Okay, in terms of the filter's quality factor, how sharp it is, and the place of its center frequency. So it is hard to get a very sharp filter at a very high frequency, right? The sort of the tail of the filter, okay, the length of the tail of the filter is sort of positively related with the center frequency of the filter. So that is why if we divide this operation into stages and use first of all a low center frequency F1 and a sharp filter there, and then take the SSB modulated signal, which now has a DC null built in, and then translate it into higher frequency, we can solve this problem. Why does it have a DC null built in? Let's look at this picture. So suppose this is the baseband signal. This is just like voice or music or something. It's between 300 to 3,500 hertz. First of all, use a 10 kilohertz carrier, bring it to 10 kilohertz. So this is, notice that this is not DSP, this is SSB. This is SSB. This part starts at 10.3 and this part starts at 9.7. What is the gap in between, the gap is 600 Hertz. This is our first stage SSB. Is this upper sideband or lower sideband?
Upper sideband.
Upper sideband, by the way it looks, right? Good. You're learning. Nice. Okay. So basically now we are going to treat this upper sideband signal as a message signal, as if this is the message signal that we're modulating, and we will modulate again. But now it already has a DC null of 600 Hertz wide. The original DC null well, it's the same, really. We haven't really, in this case, oh, I'm very sorry. Let me take this back. Let's go back. This is not SSB. Here, we've only, sorry, this is not SSB. This is the DSP. I take this back. Sorry about this. So this is actually DSP. And now we're using an SSB filter to recover the upper sideband. And now, what does the SSB signal look like? This is 10 kilohertz. And this is my upper sideband signal. This is the first stage modulator. What is the gap in between? It is 20 kilohertz. Now I'm going to pass it through a second stage. Okay, now I will use a 500 kilohertz carrier. The second carrier is the 500 kilohertz carrier. It's as if now I'm multiplying, I'm modulating a signal with a 20 kilohertz DC null. Now, what happens is, now I'm at 500 kilohertz, right? And I have this signal. Now I can easily put a filter around it, okay, to get the upper sideband again. Okay, so that is the idea of the two-stage modulator. The moral of the story is we do not have to do everything in one stage or at once. Okay, so I'm sorry I confused you in the beginning here. This was still the DSP, and we filtered the DSP using a sharp filter because the filter center frequency is at 10 kilohertz, which is not that bad. A 600 hertz DC null is okay for that. And then by this filter discriminator method, we obtain the upper sideband signal. The upper sideband signal looks like this. Now we feed this upper sideband signal into the second modulator. This time, we are raising it up to 500 kilohertz. And now, since the DC null so-called DC null is 20 kilohertz, this is a manageable DC null for placing a filter around 500 kilohertz, 0.5 megahertz. Any questions?
Can I ask a question?
Yes, please.
The reason we do this two-step thing is to increase the DC null thing so that we don't need sharp filters at megahertz, right?
Yes,
Okay.
exactly. That's it. I mean, that's just for easing the electronic design. No other reason in terms of, it's not going to give us a better modulation or anything.
Okay, thank you.
Why are we studying this? Because it is an example of how in communication systems, we sometimes break things up into stages.
Wouldn't it better to use a higher frequency first carrier to widen the band gap between the signals?
Higher frequency first carrier.
We use 10 kilohertz, but maybe, I don't know, our filter is not too sharp.
Yeah, I mean,
Will there be a trade-off?
numbers have been chosen for this example.
What
Other
I want to
numbers
say,
are possible. Yes?
will there be trade-off using a higher frequency carrier?
When you use a higher frequency carrier, the filter that you use in the first stage, the discriminator you use in the first stage, is going to have to be a higher quality filter, because the DC null in the first stage is only 600 hertz in this example. So it's a filter design trade-off. I'm sure you solved such problems in your analog electronics course. It increases the cost of the filter. But you know, increasing the cost of the filter, what does it correspond to in digital signal processing, for example? It just increases the order of the filter. It just increases complexity, if you think about it that way. That may not have meant much to those of you who have not studied digital signal processing yet, although most of you are taking it. So. Anyway, so enough about this, I think. So all of this was the first method where we first generate double sideband and then we filter one of the sidebands out. Another method is the idea of directly generating the SSB signal based on the mathematical expression that we derived. I think this is a preferable method because it's going to also suggest to us something that we can do in communication for bandwidth efficiency, regardless of doing SSB or not. So, I mean, this is going to suggest a structure to us, but first let's study this method. So the mathematical expression of SSB in time domain is m of t equals cosine plus or minus m Hilbert times sine. The plus or minus depends on whether we're doing upper sideband or lower sideband. Which one is upper? Which one is lower? Let's see. So the one with a minus here is the upper sideband one. Oops. Okay. So we need m of t modulated by a cosine and m hat of t modulated by a sine. We can obtain the sine by a 90-degree phase shift from a cosine. Okay. And basically add or subtract. So if depending on whether it's SSB or DSB, we could have a minus or plus here. Okay, so the key component, the key filter here, there's only one filter, it's the Hilbert transform filter. What kind of a filter is the Hilbert transform filter?
It phase shifted the
Exactly.
signal.
That's a 90-degree phase shifter. So the Hilbert transform filter is actually also quite sharp, if you think about it. So this is a wideband requirement that may burden the phase shifter design. So that's another thing to think about, worry about for the electronic design of these things. So let's now, well, I was going to talk about the demodulation, but I think that is going to have to wait for the next class.